Right. So last class we learned about the characteristics of living things. Specifically, we went through 7 characteristics. I'm not going to go through them again, but you should know them. And we also talk about doing science. Oh, I gotta share the screen here, otherwise it's not gonna work. There we go. Okay. So we also talked about how there are different approaches in doing science. We discussed discovery science, where you are making observations without changing the system. And when it comes to the different kinds of observations you can make, there are qualitative observations using your senses, things that you can see, things that you can touch, things that you can smell, so on and so forth. These tend to be non-numeric observations. You're not using any numbers. Okay. And then there are quantitative observations that you can make using measurements with numbers like mass, volume, density, so on and so forth, right? So qualitative observations are more subjective. It depends on the person. So it might not be very accurate in some cases. And that's why we would rely on measurements in some situations. Then we talk about how we can draw conclusions from our observations in creating some kind of generalization. That kind of logic going from specific examples to general expression, we call that inductive reasoning. Okay, then applying that generalization to specific cases, then we call that deductive reasoning. Okay, so that's where we left off last time. We started talking a little bit about hypothesis-driven science as well, where there is a process involving questioning, doing hypothesis, and so on and so forth. So just come on in. Yeah. Morning. Yeah. Come morning. So what we're going to be doing is basically understanding the different steps in the scientific method process. And it's a particularly important things for you to understand, because you will be using the scientific method in the Beetroot Lab. Okay, the Beetroot Lab is going to happening, I think, sometime in early October. Okay, so here we go. Lots of notes taking today. Please take out some paper, and we're gonna get to it. Okay. All right, so let's backtrack a little bit. The process of scientific method is used to test certain hypothesis. A hypothesis is basically a tentative answer to a question that you might have based on your observations. Okay. In our example, we said that there are plants, two plants. One is taller than the other. The question we asked ourselves was that, why is it that one plant is taller than the other? And then we came up with a tentative answer, right? We came up with a hypothesis. And some of you said maybe it's because of the different amount of sunlight. Okay. Some of you said maybe it was because of different kind of soil, and so on and so forth. So in order to test your hypothesis, we have to run an experiment. We have to design an experiment to test it. And in setting up an experiment, there are things that we deliberately changed, and then there are things we kept the same for it to be a valid experiment. Okay, so what we're going to be looking at in the next little bit are the different kinds of variables that we can have. Okay, namely, we have dependent variable and independent variable. And it turns out we also have what's called standardized variables. So we're going to be writing all that down in the notes here. Okay, so just to backtrack a little bit, the observation that we had, is that in your house, some plants grow taller than others. And then the question that we're trying to address here is, why do some plants grow taller than others? And we need to have a tentative answer for this question. We try to come up with a proposed answer to the question. And you don't necessarily know the right answer. That's why we ask the question. If we know the answer already, then asking a question is pointless. It's a rhetorical question, right? And when we write the hypothesis, it needs to satisfy two conditions. What two conditions do we need to have in a valid hypothesis? Does anybody remember? A valid hypothesis needs to be blank and blank. Yeah, please. That's right. Testable and falsifiable, right? You have to be able to run an experiment to test it, and you have to be able to potentially be wrong about your hypothesis. Okay, so what's a good hypothesis for this particular observation? Now, for this particular question, rather. Okay, sure, right. So your hypothesis might be plants receiving more sunlight will grow taller. We can test that for sure. We can be wrong. Right? Maybe it's not the sunlight, maybe something else. Yeah, but you can only pick one thing to test at a given time, okay? So now we're going to set up our experiment. When we do an experiment, we have two types of variables that are particularly important, right? We have what's called the independent variable. The independent variable, this is the variable that is being changed deliberately. Deliberately means on purpose, okay? It's being changed on purpose in an experiment. One way for you to remember this is independent is what you are in control of. Right? You get to choose what variable to change in the experiment. Okay. So if you are trying to see if more sunlight is going to result in a taller plant, what would be the independent variable be in this experiment? What is the one thing you're going to change between different plants to see whether this is true or not?
One plant in the sun near where you get more sun in the house, and then you put one plant where.
Right, so that's how you would do the experiment, right? But what would the independent variable be? What would be the one thing that you are able to control in the experiment? One thing that you're able to change deliberately? Yes, please. Exactly, right? You can choose how much sunlight each plant receives, right? By placing it at different places. Okay? So the independent variable in this case is amount of sunlight. You guys understand this? Yeah. Give me a little nod if you're with me. Okay. So I'm gonna put this back up in a bit. let me go back to the PowerPoint for a second. We had this slide about valid hypothesis, and we did the first one already. So here is a second hypothesis. Driving with the windows down will increase fuel consumption. If you were to test this hypothesis with an experiment, what would be the independent variable? What would be the thing that you were able to change to control? What about the windows? Yeah, exactly, right? So like on the test, if I asked you what the independent variable is, don't just put window. You would say like the position of the window, right? Like is the window closed or is the window open? Does that make sense? And you can control that, right? And whereas how much fuel you use, that's not something that's in your control. That's something you're trying to assess. That's something you're trying to observe, right? Like, is that going to be affected by the position of the window? Okay, so over here, let's write down independent variable. That would be the position of the window. How about the next one? The hypothesis is that taking melatonin, which is like this hormone that your brain naturally makes for you, but you can also buy it at Walmart. Taking melatonin will increase sleep duration. If you were to test this in an experiment, what's the independent variable? Yeah, the amount of melatonin taken by the person, right? Is it not taking any, right? Taking the full dose, taking half dose, whatever the case happens to be. Okay. So the independent variable is the amount of melatonin taken. All right. It says amount of melatonin taken. And that's independent variable. So in these scenarios, you must be able to identify what's the independent variable and therefore also being able to identify what the dependent variable is. Okay, we're going to get to that in a second. If you can't see my writing, just let me know, okay? Sometimes it's a bit small or they're a little bit hard to read. Just let me know. All right, so next one is the dependent variable. Okay, the dependent variable. Oh, you back in my class? Or another class? Okay, no problem. Okay, check your schedule, guys. This is GS 182, biology. Okay, if this feels like chemistry, it's not. Okay, it's biology. Dependent variable. Okay, dependent variable. This is the variable that is being measured or observed in an experiment. All this will be posted, okay? So like no need to take pictures, but it's okay if you did. So in the experiment, after changing the independent variable, you want to see whether or not it will have an effect on the dependent variable. Does changing the amount of sunlight have an effect on the height of the plant? Does driving with the window open or closed have an effect on the fuel consumption? Right? Does taking melatonin or not have an effect on the sleep duration? And so the outcome, the effects, the thing that you're trying to observe and measure in an experiment, that's the dependent variable. And so in the context of the plan scenario that we're doing, it would be the height of the plan. Height of the plan. Now, not everything can be quantified. Not everything can be measured or observed as a number. But in cases where you are able to do so, you might be able to plot your answers, plot your data rather, okay? And it's important to know when plotting your data, the dependent variable is going to go on the y-axis. Okay? And then the independent variable is going to go on the x-axis. Now, if you don't know what the y-axis and the x-axis is, don't worry. You will be learning this, I think, in math as well as in your computer course. Computer teacher is going to teach you how to plot data on Excel or Google Sheets or something like that. And then, you will know the y-axis and the x-axis. And then you will need to do it for my lab, okay? In your first lab, the Beetroot lab, you will have to plot your data. But like I said, you will learn how to do that in math class and potentially, I think computer class, right, for sure. And if you still don't know, that's okay. I'll have videos that show you how to do it. So, any question about what these mean? Okay, so what's the point in every experiment, right? Well, here, I'm gonna write for you. If you just come in, don't worry, everything is recorded. You can watch it later at home. So this is important. Okay. In every experiment, the goal is to figure out whether or not changes in the independent variable in every experiment, we're trying to see if changing the independent variable will result in changes in the dependent variable. If I change this, is it going to affect that? That's essentially what you're trying to figure out in every experiment. Okay. So let's practice a little bit. If you have the study guide, please take it out. You picked one up last class, right? From me. If this is your first class, there are handouts on the side. Okay, so in the study guide, there are a few questions here on page, I don't know, page 2. I think this is page 2. Yeah, page 2 here. We're not gonna have time to do all of them, but maybe let's do two of them. Okay, let's do 3 of them. Okay, A, B, C. Okay. With the person sitting next to you or around you, please spend 5 minutes, right, doing these 3 questions. Okay, so first one, the independent variable. If I were to test this out, I would put the students in two groups, okay? This group of students will be watching it by themselves, right? In different rooms, presumably. And then you would have another group that's going to be watching it together, right? So that would be the independent variable, okay? Either watching the cartoon alone or with others. And what are you trying to find out in the end? What are you trying to observe or measure? Well, that would be the rating of how funny the cartoon is, right? Morning. Any questions? Okay, next one. A comprehension test was given to students after they had studied textbook material either in silence or with the television on. So what's independent variable?
Study with textbook material in silence or in television.
That's right. So are you studying in silence or are you studying with TV on, right? I'm not going to write it out. Right? Dependent variable would be the result on the comprehension test. Is that okay? All right. Now, in case you missed this last class, it's very important that you study from the study guide. Okay, you study from the notes. That's important too. But the study guide, you should definitely work on it yourself. Right? Like I said, sometimes I just take questions directly from the study guide and put it on the quiz. Okay, this is not a trap or anything. If it sounds too easy, it's not. Okay, I'm telling you, do the study guide, and it will prepare you quite well for the quiz. Now, like I said, I won't have time to take up everything in the study guide. So instead, what happens is if you go on eCentennial, content, and then there's the study guide right here, right? Study guide. I'll post a link to it. You don't see anything right now because everything is hidden, but I'll unhide them. So now you will be able to see it. There is the answers. Hopefully you have better internet at home. There it is. Okay. So you just have to work on it yourself first, and then you check the answers. Okay. Don't just look at the answer because that's not the point, right? Okay. Now, sometimes looking at the answer is not enough. Like you might not understand why the answers are the way it is. So then you can click on the tutorial here. And the tutorial is basically like me explaining the thing, okay? So like it's some of the stuff that we did in class, and then what is this like? Yeah, so basically I'm going through the study guide with you, okay? So you might not need that, okay? Most of you won't, but some people like to listen to explanation, right? Okay, so you have all the tools you need to hopefully do well in the course. Any question? Okay, so content, and then study guide answers, right? Fantastic. Okay, moving on. Now, back to our experiment. We now know what the dependent and the independent variables would be in our hypothetical situation. So we would have two groups of plants. Okay, we're gonna have one group of plant here, one plant. And then we would have another plant. There we go. Oops. There we go. Okay, so this one of the plants here, it's going to be our control group. Okay, control group. It's very important to include a control group in every experiment. The control group receives no modifications, no changes. This is the default. Right? By having a control group, right, the purpose of control group is to provide, the control group provides a reference or baseline to compare with. If you only have one plant and then you give it some sunlight, and listen for a second, right? If you only have one plant and you leave it in the sun and then it grew by 20 centimeters, how do I know that's like a significant growth? Maybe it would have grown 20 centimeters on its own without the extra sunlight, right? Or maybe it would have been growing shorter or taller. You won't know unless you have something to compare with, right? That's why we need to have control. Does that make sense? So control is the baseline, it's the reference. It's the group that receives no modifications. Okay. The other group that we have is, there are a couple of names for this one. We can call it the treated group. Or we can also call it the experimental group. And this one receives modifications. Okay, just single modification. You cannot change more than one thing at a time. If you change the amount of sunlight it's receiving and you change the amount of water it's receiving, and then in the end it grew taller, you won't know whether it was the sunlight or whether it was the water, right? So you can only change one thing at a time. And what do we call the thing that you change in an experiment? What variable is that? Independent, exactly. Independent. So here is the next important thing. Another star. Besides the independent variable, everything else should be kept, should be standardized, okay? Should be standardized. Standardized mean kept the same. Between the two groups. You're only changing the amount of sunlight. Everything else would be part of your standardized variable. So if you do see a difference in the end, you know it was the sunlight and not anything else, because you didn't change anything else. Okay? So we're going to try to come up with a list of standardized variable for this experiment. Okay. So amount of water. Okay, so we're just brainstorming here. Hands up if you have some other example. We'll post the notes, okay? So no need to take pictures once again. Right? This will be posted online. So what else do you need to keep the same between the two groups? The control group and the experimental group, okay? Same amount of water. What else needs to be the same? Yeah. Amount of fertilizer, yeah. The place, you want to elaborate a little bit more? But we can't put it in the same place necessarily, because then they would be receiving the same amount of sunlight, right? But I kind of get where you're getting at. You want the surrounding to be similar, right? Okay, yeah. Type of soil. Okay, so let me write some of these down first before I forget. Type of soil, amount of fertilizer, and you know, when we say the place, we actually have a bunch of other things we can consider when we think of the place. For example, yeah, 1 second to you. The temperature, right? That would be part of, you know, what falls into the place. Yeah. Is temperature? Okay.
Yes.
If you have something else, yeah, later, yeah. Fertilizer, okay, fertilizer. There we go. Okay. Anything else? Maybe a couple more, 2 or 3. You will have to do this for the quiz, guys. So let's practice now. What else do you need them to be the same? Yes. The same plant, exactly. Same type of plant. You can't use lettuce versus spinach. Okay, not gonna work. Okay, same plant. There you have another one. I saw another hand. Yeah, go ahead.
We could introduce a different type of like an animal bug in there. Maybe.
So make sure, okay, like I wouldn't say introduce a bug in it, but make sure that they're both like maybe pest-free,
Yeah.
right? Or if one has pest, then, you know, actually it's best probably like pest-free, yeah. Because otherwise it's hard to control, right? Pest-free. One more. Yes. Put them both in the dark environment, but then we don't want both of them to be in dark, right? One dark, one sunlight, right? Yeah, so that's the independent variable. One more thing we cannot change. Yes, please. Sure, the pot size, right? Because if you ever grow any plant indoor, you would know some plants would only grow as big as the pot. Okay, if you have a small pot, it's gonna stay like that. Once you repot it to a bigger one, then it grows taller, right? Bigger, right? So maybe that has an effect on it, right? So we'll say pot size. All right. So I want to emphasize the importance of having all these things kept the same. You need to keep all these the same so that when you see a difference in the height and the end, you know it was caused by the sunlight and not any of these things. Make sense? If you want to test whether different amount of water will change the plant's height, then the amount of sunlight will be on this list, because then you're only changing the water, right? In any experiment, you only try to change one thing at a time so that you know if you observe any differences, it was caused by that change. All right, let's go back to the PowerPoint slides. If we have time in the end, we will practice more. So suppose we go ahead and we set up the experiment. We have, I can't hide that thing, sorry. Let's say we have the 6 hours here. That would be our control. Okay, that's like standard amount of sunlight. And then this would be the treated group. Right, they will receive 12 hours of sunlight. And of course, I am oversimplifying the situation here. in a better design experiment, maybe you have a few more treated group, right? Maybe you want to have like 18 hours, maybe you want to have 24 hours. Okay, but in a very simplistic way, control and treat it. We talk about the standardized variable already, right? Humidity, all right, so on and so forth. Initial plan height, okay. And then you can predict your result. If my hypothesis is correct, or if it's incorrect, what kind of result am I expecting? So if the hypothesis is correct, then the plant exposed to more light will be taller. That's very self-explanatory. If it's incorrect, then I would expect them to have similar height, or more sunlight will actually make it shorter. That's possible. Some plants don't like sunlight. Okay, they don't like as much sunlight. And so you have to know what kind of result would either validate your hypothesis or would reject your hypothesis. These are the results. 6 hours, it grew from 12 centimeters to 13, only 1 centimeter change. 12 hours, it grew by 6 centimeters. And so based on this result, we can say the experimental data supports the hypothesis. More light will make the plant grow taller. Okay. What kind of result are these? Are these qualitative results or quantitative results? If you think it's qualitative, put up 1 finger. If you think it's quantitative, 2 fingers. Show me. Okay, good. I feel better. These are numbers, so they are measurements. They are quantitative. Okay. Now, again, this is oversimplification. If somebody actually do this experiment and then they make this conclusion, it's actually really bad science, okay? Because there are only 1 plant and 1 plant. Okay, that's very small sample size, right? In a realistic situation, you need to have much bigger sample size. Okay, you can't just give a vaccine to 1 person and be like, okay, it works on you. Let's now give it to billions of people, right? That's very unsafe science, right? In the real life situation, concluding an experiment will often lead to more questions. Now that we found out sunlight has an effect on the height, maybe the next step is to find out the optimal amount of sunlight. Okay, maybe 12 hours is going to make a taller plant. Maybe 24 hours is going to make an even taller plant. Okay, once you figure out, oh, if 24 hours gives the tallest plant, maybe we can change the intensity of the light. Okay, like really bright light, because you can have like, you can dim the light, right, at different levels, right? So there's always more questions that you can find out. Once you find out a vaccine works, maybe you need to find out the optimal dose. Right? How many times do we give the people to achieve maximum efficacy, right? So more questions after you find a conclusion. It's just kind of like a cycle, right? All right, let's do this concept chart question. All right, again, to do these, you just show me your fingers. If you think it's A, put up 1 finger, B, 2 fingers, so on and so forth. Look at me after you put up your finger so I can tell you whether you get it right or not. Good. Good. Not quite good. That's good, yeah. And anyone else? Good try. Yes, that's right. Anyone else? And you gotta look at me after you put a finger. Yeah, not quite. Good try though. Good try. Yeah, that's good. That's good. 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 Anyone else? All right, so I'll take this up. Producing a tentative answer. A tentative answer to your question, that would be hypothesis. A hypothesis. Okay, the experiment is to test your hypothesis. Okay, so write down. Hypothesis is tentative answer. Some people call it educated guess, right? Testable, falsifiable. And I want to remind you to study these concept check questions as well when you're preparing for a quiz. Sometimes they end up showing on the quiz and the test. And let's do one more. What is this one? Good, good. Yeah, very good. Yes. Yes. Yeah. Yeah, I think most people got it this time. The set of actions or observations designed to test the hypothesis. If you were listening to me a minute ago, you would know this is experiment. Okay? So some questions will be straightforward like this. Other questions will be a little bit more complicated like that, okay? It's a mix of questions. But like I said, I'll tell you exactly what's on it. I am pretty fair when it comes to the test. Very transparent. There's no surprises. What time is it? Okay, we got time. We're going to spend the next little bit talking about the kind of like the origin story of scientific method, right? So this methodology of making observations, asking questions, designing experiment, like where did it come from? Well, we're going to go all the way back to the early 1900s, okay? Prior to the mid and late 19th century, the origin of life, well, I mean, that always has been a question, but particularly during that period, the origin of microorganisms in decaying matter was hotly debated, okay? There are some people who believed in a theory called spontaneous generation. The theory basically goes like this. Living things came from non-living things, right? And there are observations that supported this view. For example, if you leave a piece of meat outside and you come back to it a couple of days later, then you would see there are flies and maggots on the piece of meat. So people are like, see, the flies and the maggots, living things, they are spawning from the meat, which is non-living. Right? So they take that as evidence of spontaneous generation. Now, you might look at that and you're like, that's ridiculous. We know that's not true. But remember, this is like hundreds and hundreds of years ago, right? What we know now as common knowledge is not necessarily true back then. There are other phenomena that further supported the idea of spontaneous generation. And those phenomena happens nowadays as well. I never seen it myself, but I did a Google search. And every now and then there will be fish raining from the sky. And this happens in the past. People would see that fish, and sometimes frogs would be raining from the sky, and they'd be like, spontaneous generation, right? Fish is living, alive, and the sky is not, right? So if you Google it, these are real, okay? Texas witnessed a rare weather phenomena as fish rain from the sky. It happens in Mexico, it happens in Malta, even in Australia, okay? Does anybody know why this happens? You've heard of this before, by the way? No, it's the first time, yeah? Okay, anybody want to guess why that happens? Or like, this is not real, I'm just like messing with you guys. Okay, so basically, it's these water spouts, okay? Water spouts is like a tornado, sort of, okay? That goes through bodies of water. And as it does that, it scoops up some fish and whatnot, okay? And then because of the powerful wind, it actually sends them inland and it rains from the sky. But it's basically just like, you know, scooping them up and then pouring it out on land, right? But people didn't understand weather pattern in the past. And even us, right? Like we might not have heard of these things, right? Until your teacher shows it to you. So they took that as a sign of spontaneous generation, okay? My other class telling me there's a movie called Sharknado. They say, I don't know if you guys know, right? It's pretty much like this, but like it's like raining sharks instead of fish. I don't think that's possible because sharks are pretty big. Right? If it's able to scoop up sharks, then, you know, maybe it's going to be raining ships as well. In any case, in the 1600s, there was this guy. His name was Francesco Redi. Okay, just remember his last name, Redi. He wanted to test the idea of spontaneous generation. Okay, so he actually is the person who's credited with coming up with the scientific method. Okay, so we're gonna take a look at what he did. He made an observation that many people did. Flies and maggots can be seen around pieces of meat that are left on the counter, okay, or left outside. And the question is, where do flies come from? Is the rotting meat being transformed into flies? All right, so tell me, after observation and question, what's the next step? We're going to try to answer our own question, right? And what step is that? Hypothesis. That's right, hypothesis. So his hypothesis was that only flies can make flies. Rotting meat cannot be transformed into flies. A logical hypothesis. You can test this, and he could be wrong. Testable, falsifiable. So we're gonna take a bit of a note with the spontaneous generation here. Okay, lots of writing today. So this is Rady's experiment. We gotta pass the attendance around as well. I'll get to know you guys soon enough, okay? Like I have to recognize the face first before I put a name. Usually by week 2 or 3, then I would know your name, okay? All right, so Rady's experiment. The legend goes like this, okay? I mean, I don't really know if this is exactly what he did, but some version of it. Okay, he had 3 jars. Okay? 3 jars. So there are 3 jars, and in the jar, he put some meat in it. So the first jar has no coverings. No coverings. It's just exposed to the air. Next one has a net covering. And the next one has it's a sealed jar. I don't know what he sealed it with, but it's completely covered. All right, I think the attendance is causing a bit of confusion. So just pass it like this. Okay, pass it sideways and then to the back and then sideways to the back. Okay. All right, so that's the setup. What's the independent variable in this experiment? What is the only thing that he changed? What's that? Covering, the type of covering, right? Okay, like write a few words on the test. Don't just say covering, right? Independent variable. Type of covering. What about the dependent variable? What is he trying to observe in the end? He's gonna leave this outside for a couple of days, and then at the end, what is he trying to observe?
How the meat rottens,
Okay.
or how bugs happen.
Okay. Anyone else? Just pass it along. What did you do already? Anyone else? What's the dependent variable? What's he trying to assess here? In like 3 or 4 words. Yeah, exactly, right? So dependent variable would be the presence of flies and maggots. Yeah, flies and maggots. Okay, I'm gonna give you 3 minutes. Talk with people around you. I need a list of standardized variables. All right, he can only change one thing, which is the type of covering. What would be everything else that he needs to keep the same? Okay, 3 minutes, talk about it, and then I'll ask you to tell me. All right, go, go, go. All right, let's hear it. What are some of the things that he has kept the same? Just yell them out. Sure, temperature. What else? Type of meat, that's right. If you're gonna use beef, then you use beef for all of them. And more important, like the age of the meats as well, right? They all have to be like, purchased at the same day, on the same day or something, okay? Anything else? What do you mean by that? Time for?
How long it's varying.
That's right, the duration, right? How long do you leave this out for, right? Okay, they have to be all left outside for a week or something like that. Okay, maybe 3 more, please. Yeah, container type. Okay, same size. Got to clean it first. Okay, same material. 2 more, please. Sure. Size of the meat. 1 more. There are actually a lot more things, but 1 more. Yeah, the container type will leave it in there. Anything else? Yeah. Sure, right? So the temperature of the environment and maybe 1 more thing about the environment. Can you think of? Sure, humidity. Okay. Now, what's the point of keeping all those things the same? Well, in the end, if you do see some flies in some and not others, then you know it was caused by the covering, right? And not anything else. Now, I hope we all know the results of this. If you don't know, I encourage you to try this experiment yourself. Just don't send me any pictures afterwards. First one, flies or no flies? Yes, okay. I can tell you there will be flies, okay? And then there will be maggots crawling all around, okay? This is going to be gross. Net covering, flies or no flies? No flies on the meat, but actually there will be flies buzzing around, okay? Like there might even be some maggots crawling on the net, okay, but not on the meat itself, okay? Seal jar, nothing, okay? The meat might be gross inside. It might be, juicy and whatnot, juicy in a bad way, but there will be no flies because it's sealed, right? Okay, so that's the experimental result, and he concluded that flies do not came from meat. Okay, only flies can produce flies, right? And that is the conclusion that we all expected. Okay. You might think, like, come on, do you really need to do an experiment to test that? Well, I'm sure like in a couple hundred years later, people look back at the things that we do, they would probably say the same thing. Okay, so conclusion, only flies can make flies. Meat cannot be transformed into flies. All right, we're gonna take a 5-minute break. Do try to stay with 5 minutes. Okay, it's not a Tim Horton break. Just like stretch your legs, okay? Because we will resume at 9:37. Okay, so see you guys in a bit. And what do you know? It's 9:37. Let's keep going. So that was Brady's experiment. And you would think from something like this, people would be convinced, right? Like living things don't come from non-living things. Some people bought into it, right? Some people thought, oh, okay, well, I guess spontaneous generation is not correct. But others were not so convinced, right? Some argue that maybe spontaneous generation is not applicable to big organisms like flies and maggots, but it could still be true for microbes. Microbes are microorganisms that we cannot see with our naked eye, right? And so in the late 1800s, this guy, name is Louis Pasteur. He did another set of experiments that would definitively show that spontaneous generation is not correct. You might not have heard of Louis Pasteur, but there is a technique that he invented that are still being used today, and we benefit from it. Do you guys know what technique I'm talking about? Pasteurization, exactly, right? When you drink milk and when you consume honey, they are pasteurized product, okay? You should not drink raw milk, definitely not the animal kinds. Raw honey, some people do it, okay? But it's there's a certain level of risk to it, right? So by pasteurizing it, you kill off all the microorganism, and he's credited with the process. So just a very short note on what his experiment looked like. Let me turn down the volume here. Pasteur. Experiment. All right, so he instead of jars, he had these flasks. Okay, these are called volumetric flasks, and they do look like that. And he had two kinds. He had an open top. That's your open top flask. And he has one that has a special neck connected to it. Okay, this is called a swan neck. Swan neck flask. He put some broth in it. Let me find the right color for the broth. Okay. Some kind of maybe chicken broth or something. So both flasks were boiled initially to kill off existing microbes. Okay, so by boiling them, the broth are going to be sterile initially. Sterile means like no living things in it, right? Sterile. So this would be like sterile broth. Initially. Then he left them outside. I don't know how long, a couple of days maybe. And then afterwards, he looked at the broth. He looks into the broth with microscope probably. Do you expect this to have anything living in it? Or do you expect this to have something living in it? Which one do you think has stuff living in it after a few days? The open top or the swan neck? Open top, right? Okay, because then we know now. That's why we put saran wrap on our food, right? That's why we put them in the fridge and whatnot, right? Because it's open top, things have fallen and start growing, right? Okay. So after a few days, only the open top flask has microbes in the broth. Okay, of course, the swan neck, the things fall in, but they're all trapped in the U here. They can't crawl up, right? And so the broth remains sterile. Okay, so that definitively showed that spontaneous generation is not true. It's not true for flies and maggots. It's not true for microorganisms. I want to ask, show me the finger, 1 or 2. 1 or 2. Which one is the control group in this setup? Is it 1 or is it 2? Show me. What do you think? Okay. Okay. Which one is the control group? Which one is the one that you didn't do anything to it to change it? Okay. Yeah. Okay. Most people got it right. This would be the control. This is the one that, you didn't put a special neck on it, right? This is just the default, right? And this is the one with the modification. Control. Treated. Any questions? Excellent. All right, another concept check question. Show me your answer. That's good. Yeah. Not quite. Try again. Not quite. Yes. Good. Go back. Yeah. Yes. Anyone else? Looking for the independent variable, the one that he changed. Very good. Yes. Anyone else? Mhm. Good. Any last try before I take it up? All right. So independent is the thing that you change. The only thing that's different between the two flasks is the opening, right? Is the neck, right? So the answer is type of flask used. Okay. The dependent variable would be the presence of microorganisms. Independent, dependent. How about type of broth used? What kind of variable would that be? Standardized, exactly. You have to use the same type of broth, right? Flask was initially boiled or not, that would also be part of standardized. They both need to be boiled. This is the wrong experiment. Right? This is Rady's experiment. Okay. All right, we don't really have time to go through this, but there's something to think about, okay? On the internet, there is this claim, right? Someone posted this and found it online. Say, day one, we have two happy-looking plants, and the person claimed that when they're gonna water one with purified water, and then the other one, they're gonna water it with microwave water. Okay, not like boiling hot and pouring, so you're definitely gonna kill the plant, right? Okay, so like you microwave the water, you let it sit back to room temperature, and then you use that previously microwave water to water the plant. You understand that? Okay, and then they claim after 9 days of being watered with the microwave water, you kill the plant, and therefore you should throw your microwave away, because if it can kill the plant, it's probably not too good for microwaving your food, right? So that is a big thing apparently. Anybody heard of this before? No, yeah, they say radiation, right? Things. What do you think? Do you think this is true? If you think this is true, no judgment. I just want to know what you think. Okay. My other class was half split. Right? What do you think? Do you think this is true? Thumbs up for true. Thumbs down for probably not true. What do you think? I'm just curious. Do you think the microwave water will kill the plant? Thumbs up. Thumbs down. Show me. Participate. Okay. Some of you are like, I don't know. Sounds sounds legit, but a little bit fishy as well. Okay, so that's something you can find out, right? That's something you can test on your own, right? But I'm just gonna tell you, okay? It's not true, okay? Yeah, this is not true, okay? You can microwave water as long as you cool it back down and you don't pour the boiling water on your plant, not gonna kill them, okay? Microwave works by causing rotation of water molecule. As the water molecule rotate, it gives off heat. That's why you cannot microwave something that's completely dry. You ever notice that plates don't really get hot? It's the food that gets hot. There's no water, no water molecule in the plates, right? So there are no what do you call that? No radiation as well. Okay. You know how your microwave has those black mesh at the front? Okay, the little, do you guys know what I'm talking about? Little black taping thing at the door. That actually is meant to break off all the microwaves so they cannot escape. Right? When I was growing up, my parents told me not to stand next to the microwave when it is going, because it will cook my stomach. So I got really scared, but I found out that is also not true. Okay. Anyways, so this is a fun experiment that you can, think about, right? What's the independent variable? What's the dependent variable? So on and so forth. Now we're gonna move on and talk about experiments that involve human subjects, human testing. Okay. Whenever we include humans as part of the testing, as part of the experiment, things get a lot more complicated. Okay. When we deal with humans, we need to follow ethical guidelines that are set up by committees, and these guidelines tend to vary from countries to countries, but generally they involve obtaining consent from the participant, okay? And these are consent that has to be given to you voluntarily. You cannot force people into doing the experiment. After all, then that's not consent. You cannot coerce them into doing it, right? They have to be completely voluntary. And the consent has to be ongoing. Right? If someone agrees to participate in an experiment and then they change their mind midway, you gotta let them go, okay? It's not something that you sign up for and then, it's forever, right? There has to be reasonable measures taken to protect the participant from both physical and mental harm. These are just some of the examples of ethical guidelines that you have to follow when you design an experiment. Actually, they need to submit a report to an ethical board, usually, that would take a look at the experiment and make sure that it adheres to the guideline before they are being approved. Another complication when it comes to doing experiment involving human is that humans have biases. Okay, there are some personal bias or psychological biases that you might not even be aware of. And in order to minimize these biases in the experiment, we have to use what's called a placebo. Okay? A placebo is a sham treatment. It's not real. Okay? you might tell them is real, but in fact, it's not real. So you might give them a pill, and instead of the actual experimental drug, you're just giving them, people call it like a sugar pill. Okay, it's not supposed to do anything. Okay, but they don't know that. The whole point of the placebo is not to let the participant know, right? Okay, you give it to them, you don't tell them what it is, and then you evaluate the results. Okay, so the placebo is going to help us minimize the effects of psychological bias and things like that. Let me give you an example. My younger daughter, she's really dramatic when she's like younger, okay? Like if she falls down at the playground, no bleeding, skin is intact, just like a white scratch, and she would cry her eyes out. Oh, it hurts, I can't do this anymore, right? So then to stop all these drama, I always carry some Band-Aids with me. And then I just put a Band-Aid on. It's like, oh, it's good now. And then she go back to play, okay? Did the Band-Aid do anything? I guarantee you not, okay? It just, it's just a Band-Aid there. It's a psychological blanket that they have, right? It's the same concept as people say, kiss it better, right? You guys familiar with that phrase? Sometimes they have a little scratch and then the parent kisses it and then it feels better for the kids. I wouldn't recommend it. If anything, you would actually make it worse by kissing it because like you are like introducing bacteria and stuff like that. But it's the same kind of psychological effect. You understand? It's like, oh, there's something that's being done, so I feel better about it. Okay. And these kind of psychological effects is important when you do an experiment because it significantly skew the results in some cases. Okay. And that's why you need to have a placebo. Do you guys all understand what a placebo is? Okay, if I ask you on a test, what's the purpose of a placebo? You would say minimize bias, okay? Psychological bias. Now, I'm going to give you an example. This example has nothing to do with experiment, okay? So don't tell me this on the test when I ask you what a placebo is, okay? This is just like I misread my own notes. There is another slide here that talks about setting up an experiment. I actually don't have to write it up for you, okay? I'll just tell you what it is. It's very simple, okay? So like, let's say I want to test the effectiveness of a vaccine, right? Okay, so I would divide people into two groups, okay? Naturally, one group would receive the vaccine, right? Okay, and what would the other group receive? Yeah, normally we would say they receive nothing, right? Because it's the control, right? Okay, but because we're dealing with humans, they would be receiving the placebo instead. Now, in this case, you're not so much trying to minimize psychological bias, okay? Because it's not something that you can, change the results by thinking about it, right? You cannot be like, oh, I receive a vaccine and therefore I'm more protected. I know I'm more protected and therefore you are. It doesn't work like that, right? Okay. So in this case, the placebo is for the people who are doing the experiment. We want to minimize their biases. Okay. So it's not always just bias in the subject. Sometimes you're trying to minimize the bias in the person who's doing the experiment. Okay. So what is exactly in this placebo? Well, it would be all the same ingredient as the actual vaccine minus the active ingredient. Okay. Do you guys know what kind of vaccine you received during the pandemic, if you had one? What was this new technology everybody was talking about? Yeah, it's a COVID vaccine, right? But then, like, what's the active ingredient in it? Do you guys remember hearing about it? The mRNA vaccine, does that ring a bell?
Oh,
No, yeah, maybe. Okay, anyways. So if you don't know what the mRNA is, we'll talk about that in the class. But that's the active ingredient, okay? So in the placebo, you would have everything except for the messenger, except for the mRNA. You guys understand that? Okay. So then you would give these people the blanks, so to speak, right? The placebo, and then you would see what the results are. Okay, so instead of having a control group that receives nothing, you will have a group that receives the placebo. Okay, so this is an example in another situation that uses a placebo. It's not related to experiment or anything like that, okay? It has to do with this birth control contraceptions, okay? This contraception. The name of the contraception is called Freya 28, and it comes in a pack that looks like this. You get 3 weeks of the contraception and then 1 week of placebo. Okay, so these are just like blank pills. They do nothing for you. Okay. So why would they include a week of nothing in the product? Like, I mean, I'm paying for the full price. Shouldn't I get like all the active pills? Why do they include a placebo in the package? Anybody have any ideas?
So the woman could get her cycle.
Yeah, exactly, right? So people who are on contraception, sometimes they choose to be off the pill to have the a menstrual cycle, right? And the pills actually help them keep track of time. And so when the person gets off the pill here, instead of just trying to keep track of the day herself, which could lead to confusion and then you miss the next cycle or something like that, right? You keep on taking the pills, right? Just as a reminder. So when you get to the end of it, you're like, oh, I should start the next pack and I should be back on the pills, right? So this is just placebo pills for keeping track of time. Okay, are we together so far? And so here, no? Okay. So these are contraceptives. These prevents the person from getting pregnant. Okay. And then after 3 weeks, they will switch to the placebo, the pills that do nothing. And that will allow them to have the period, basically. Okay. And after the period, after they finish the 7 green pills, then they could start the next pack and then they will be back on the contraceptive. Okay. So this helps them keep track of time. The company messed up. They made a mistake with one lot where they switch the green pills and the white pills. So people who bought that lot of the drug, they get 3 weeks of green pills and 1 week of white pills. Okay. And that's really bad, right? If you, especially if you're not familiar with the product you're buying for the first time, you wouldn't know the green pills are the ones that are not working. And you would be taking these blanks thinking you are on contraceptive when you are not, right? Okay. So the company found out and then they issue a recall and they advise people who are on the the drug needs to go on emergency contraceptive because essentially the pills are not working. Okay. So that's what placebo can be used in a real life situation other than an experiment. All right, let's keep going. Blind versus double blind. In a blind experiment, the subjects, the people who are being tested on, they don't know what kind of treatment they are receiving. Okay. They receive something, but they don't know if it's the actual thing or if it's the placebo. Okay. And that, as I told you, is going to help minimize the bias. But the gold standard in research, especially when it deals with medicine and things like that, it's going to be a double-blind experiment. In a double-blind experiment, the subjects don't know what they're receiving, but the person who's giving the pills or the test, they also don't know what they're giving. Okay, so in the single blind, only the subject is blind. Right, the scientists know what they're giving, but in double blind, they both don't know. Okay, and that's important because sometimes pharmaceutical companies have an invested interest in their products. They want it to work, right? So that they can sell it and, make a profit from it. Right? So we don't want people who are doing the experiment who has conflict of interest to know what they're giving. So when they evaluate the result, it would not be subjective. Okay, so in these cases, so who knows, right? Who knows what they're giving? It's going to be some third party that's overseeing the project and they have no invested interest in the situation. Okay, do you guys understand the difference between the two? Okay. Double blind is the gold standard. Okay. All right, so I want to go through this with you and see if you understand it. Let's say I have a new pill, okay, new drug called sleep, and it's supposed to help you reduce the symptoms of jet lag. A jet lag is what you have when you go from one time zone to another, right? When you can't sleep, you feel groggy, headaches, whatnot. So in the control, in the placebo, they are given a pill, but not the actual drug. Okay, you don't tell them what you give them something, right? And then in the treatment group, they receive the experimental drug. This is the result. Do you think the drug worked? Do you think the medication helped reduce the symptoms of jet lag? Thumbs up if you think it does, thumbs down if you think it does not. Based on this result, does the drug work? Okay. Okay, anyone else? Works or not work? Interesting. What is that though? Like, is that good or not? Okay, so it's a little bit of half here. I'm surprised. But that's okay. That's what we have to talk about it, right? Okay. So let's backtrack. Placebo. Is the placebo supposed to do anything for you? No, right? It's like it's like candy, right? It's not supposed to do anything. So if you're experiencing jet lag and you take candy, do you expect the candy to help you reduce your jet lag? No. That's why people in the placebo group, it's lots of jet lag symptoms, right? 80% of the people in the placebo group has jet lag symptoms. That's what you would expect, right? Because they're not receiving any treatment. They think they are, but they're not, right? Okay. When they take the drug, though, fewer percentage of people experience jet lag. Right? So that actually tells you by taking the medication, it's going to help you reduce the symptoms of jet lag. So this actually is an effective medication. Do you understand? Because only the drug reduce the symptom, not the control, not the placebo. The placebo is still very high. Okay, these are the people who receive nothing, essentially. Of course, they're going to have symptoms of jet lag, right? Yep. Okay, that's a great question. Right? Like here you see 80%, right? Like how come it's not 100%? Well, when it comes to things like, jet lag, right? Some people are just naturally not affected by it, right? So maybe that 20% of people are on their own, not affected by jet lag, right? So that's why, it's not 100%. But the question is like, is there like a cutoff? Like, what if this is 80% and this is 60%, right? Is that still effective? Is that basically what you're asking? Yeah. So like, you in real life, you actually have to do math, to do statistics. Well, if the treatment is even lower, then it would be okay. It would still be effective, right? But like if the treatment is like, let's say 70%, 60%, then you won't be able to tell you. Yeah, right. Then you would actually have to do math to figure it out, right? So like statistics is something you will do in a second semester math. But that's what it comes down to. All right. How about now? How about now? If the result look like this, then do you think the drug is effective or not effective? Effective, not effective. All right. Yeah. This is telling you the drug is not effective. Okay. Hear me out and try to understand it. Look, when you give them the placebo, the sugar pill, right, the thing that was not supposed to do anything, it helps them sleep better as well. It reduces the symptoms of jet lag. Right? And then you give them the drug, it also reduces the symptom of jet lag. So candy performed just as good as the actual drug. That means the drug is not doing anything special, is it? Okay. So if the result look like this, then it suggests to you the jet lag symptoms are nothing more than psychological effects. It's just in your mind, right? So if you give them something and you tell them it's going to help you sleep better and deal with the jet lag, the person feel better. The person's like, oh, okay, I got this pill. It's going to help me. And therefore they sleep better. Right? It's almost like a self-fulfilling prophecy, right? You understand? So based on the result, if it looks like this, then it's going to be effective. If it looks like this, then it's going to be ineffective. Okay. All right. We're almost there. Hang in there, guys. Another concept check question. What do you think? Good try. Anyone else? Not quite. That's good. Mhm, mhm. Not quite. That's good. Anyone else? Give me something, guys, so I know whether you guys are getting it or not. Any last try before good. That's good. Good. Okay. We are testing this drug on pregnant mice. Okay. So anything with male mice will not be the answer, right? Okay. And anything with non-pregnant mice is also not going to be the control, right? Okay, yeah, that's correct. Yeah. So do we for the control, do we give them even more drug or just the saline? Just the saline, right? Remember, the control, the placebo is everything but the active ingredient, right? Okay. Now that we understand how science works, right? How you collect data and independent variable, and all that stuff. We can use that knowledge to evaluate things that we find online, right? Sometimes we have to understand correlation between two variables does not imply causality. Correlation means if one goes up, the other would also go up, or if one goes up, the other goes down. Like there is some kind of predictability between the two things. That's called correlation. But that does not imply cause and effect. Okay? For example, people who are stressed out, according to this graph, people who are more stressed out are more likely to catch a cold. Some people might conclude that stress, therefore, causes cold. But the correlation, like I said, does not necessarily imply causality. Causality means cause and effect relationship, right? Because there are other things that could cause a person to be stressed. Maybe a person have other illnesses, poor diet, little exercise, little sleep. All these things can cause a person to be stressed out. And all these things can also, weaken the immune system and cause a person to be more susceptible to catching a cold. And so it's not necessarily that the stress is causing the cold, but maybe there is some underlying factor that's contributing to the frequency of cold. And the thing is, when you look at a lot of data at the same time, a lot of times you will just by chance find some correlation. Okay, just by chance you will find that this increase and that also increase. There's no direct relationship between them. It's all just by random chance. And a lot of times these things get blown out of proportion, especially on social media. There is a website, you can visit it, during your break after my class and whatever you have next. It's called various correlation. It shows you random stuff that have strong correlation with each other, but has absolutely no cause and effect relationship. Okay, this one, the red line is per capita cheese consumption, like how much cheese a country consumes. And the black one is the number of people who die by becoming tangled in their bed sheets. That apparently happens. And you can see there's a strong relationship, strong correlation. The two lines are almost following each other, coincide. But does eating more cheese actually cause you to be more likely to be tangled by your bed sheet? Like very, very, very unlikely, right? Okay, so just because two things are correlated does not mean they cause one another. And so I did a random Google search and I just looked for articles related to coffee consumption, and I found a few ones here. Okay, so you can see here it says drinking more coffee might reverse liver damage from booze. So people who already drinks coffee, loves coffee, they look at something like this, it confirms their belief, right? And then they're like, yeah, I knew it. I knew drinking coffee is good for me. And then they share it to all their non-coffee drinking friends, right? This is good, right? And then you have something like this. Coffee consumption in either parents may raise miscarriage risks. People who don't drink coffee look at this like, I knew drinking coffee was not good. I'm so glad I didn't drink coffee, right? And then they send it to all their friends, right? My point is, back to what I was saying. If you look at a bunch of data, okay, like coffee consumption in one column, and then you look at a bunch of other things, okay, like, liver damage, miscarriage rate, colon cancer rate, lung cancer rate, graduating from college, a bunch of other stuff. Eventually, just by chance, you will see something relates to something, okay? And many times that's what's being reported in the media. And people don't have time or they're not interested in looking up the actual study, right? And then they just share a lot of these headlines, right? And that what's contributing to, a lot of the misinformation that you see. If you look into the study behind it, I mean, I haven't, to be honest, but if you do look into it, then you might want to look at the method that they use to come up with that conclusion, okay? Who's funding the research, right? Maybe it's the alcohol industry that's funding the research, right? And then there are certain bias that are inherent in the research itself, right? Because naturally, the alcohol industry wants you to think that way, right? So that they can continue to sell, right? To be more cynical, maybe it was a partnership between the alcohol industry and the coffee industry, right? All right, let's boost the sale together, right? My point is you have to look at the study to find out how it was conducted and who actually is doing the experiment. Okay, don't just say some study shows this, some study shows that, because many of times these are just nothing more than correlations. So how do you evaluate your sources? Well, you don't have to do any research paper for my course, but maybe you have to do it for some of your other elective courses. And when you do your research, there are primary sources and secondary sources. Primary sources are often original documentation or original research written by the person who's doing the experiment, written by the person who's coming up with the actual testing. And these tends to be more reliable, okay? So you will find them in academic research paper. These paper often will be fact-checked by other peers in the fields, other experts in the field to make sure that it was done properly. Now, does that mean primary sources are always correct? No, there are numerous cases where people fake their data, they fabricated data, and they were caught later. So it's not 100% foolproof, but still it tends to be generally more reliable than secondary sources. Interviews, reporting live, as seen, all these are considered as primary sources. Secondary sources are interpretation summaries of primary sources. So that includes encyclopedia, textbooks, magazines. And when we try to get information from secondary sources, again, we have to pay attention to who's writing it, okay? Even if you hear it from the news, it might not be without bias. You might know, like in Canada, right? In the US, people say politics have like right wings and left wings, right? And some stations, some news outlets are more leaning one side over the other. So when they present certain news to you, they present it from that perspective, from that angle, and you might not be getting a completely unbiased view of what you're looking at, right? So that's basically the end of the lecture. When do I see you guys again? Wednesday, right? For Wednesday, you have to print your own notes, okay? I'll post an announcement to show you where to get it. But just before you go, okay, so when you go to the course homepage, I'll post a thing here. Just a reminder, there is an archive that you can get all the lecture recordings, especially if you missed the first class. Right, you can watch it from the archive. Class notes, I will post it there. And if you haven't already, please try the self-quiz as well. For the notes next week, go to content. Just stay put. Okay, 2 more minutes. Okay, I'll let you go, I promise. Lecture, and then lecture 2. Right? You need to print the lecture 2 notes for next class. All right?
All three?
One of these and then the study guide as well, okay?
So all three.
No, these are the same thing. Yeah, these are PowerPoint and this is the, yeah, 6 slides per page. Okay, that's it. Thank you. See you guys.